Okay, so once again, I think this was obvious. This is a little less obvious, but we're going to work out why. We're using Bernoulli's law and using the before of Bernoulli's law at the surface up here. So this is like 1, and then this is like state 2 right there. Now, obviously, I can just use this twice, once for B, once for A, but it's the same idea. Does it make sense to you that the water at the surface has potential energy? Because it's going to fall and then come out of the hole, whether it's A or B. Now, if you have a tank of water, okay, well, let's talk a big tank, like, I don't know, 3 meters in diameter, okay, and then you punch a hole in the side with a screwdriver. Do you think that you'll be able to see the water on the surface dropping? Yeah, probably not, right? I mean, that would just be so slow, you want to kill yourself. Do you get what I'm saying? It's going down so slow. Even though the water on the sides shooting out, because of the ratio of the sizes, right? If this area is 1,000 times bigger than this area, do you see that this velocity is 1,000th of that one? Remember, because A1 V1 equals A2 V2? So, does it make sense to you that it's like the top's not moving? It's moving so slowly that we can disregard the kinetic energy. You get what I'm saying there? So it's like this is dropping so slowly that we can just disregard kinetic energy. Now, when we're talking about in the tank, the water in the tank. Can the water in the tank drop any lower than the hole? Do you see why the answer is no? If there is a hole, the water's going to fall out the hole, right? It can't go below the hole. So it has no more potential energy. Because remember, potential energy is the energy of, like, whatever, like about to fall. So this is nothing. Now you'll see what we have. We can cancel out the rows because it's obvious the same stuff. And we get V is the square root of 2GH. Doesn't that look familiar? Yeah, chapter 2, chapter 6, I think. About energy. No, 5 and 6, whatever. So we've got energy there. We've got time here. Both are square rooted, right? So if you double one, it like affects the other correspondingly. Basically, the argument here logically is the hole that is closer to the surface has the lower velocity. But because it's closer to the surface, it's farther from the ground, which means it has a higher time to fall. And so what ultimately happens is the lower velocity falls longer, which makes it land at x. Whereas here, the higher velocity falls a shorter amount of time and also lands you at x. That's why that could work. So could that happen? Yes. And if you do this, what you'll see is an equilibrium point, right? If you took a bucket and poked 2 holes in it and then lifted it up in the air, what you would see is the streams come out and then cross at some point. Because it's not like this is going to happen forever, right? No matter what the height is. Because as the height gets bigger and bigger, then the times approach each other. Does that make sense? Do you get what I'm saying? Like, you know, when the height's there, maybe the time is like 30% different. But if this height is close to infinity, then the time is almost the same. Because it just takes forever to fall. So what happens when the times are the same is that the one with the faster velocity is going to go out farther. So they'll shoot out and cross at some point. And we're just saying this is where they cross. How is that possible? It's possible because of this logic. And the logic says the higher hole falls longer, therefore the lower velocity times the longer fall gives you the same distance as the faster velocity times the shorter fall. And that's that whole tamale. I have seen this problem